Okay, so I think, yeah, Ramakrishnan, you are there.
Yes, sir.
Should we start?
Yes, sir. We can start.
Yeah, okay. So today's session also will be on this week's content, so which is welding part B. Um, so my first question is on matching the following of different kinds of joining techniques, where there are diffusion, ultrasonic, FSW, and explosive welding. So if you want to match these kind of joining with these things, what will be the uh, perfect match, right? So what will be the diffusion bonding thing? So for diffusion bonding, it's basically some atomic diffusion happens in diffusion bonding. So if you see diffusion bonding, it is a solid state welding that produces coalitions of faying surfaces by application of maybe some pressure at elevated temperature. And the process, it does not involve any kind of macroscopic deformation, but there will be some kind of if you see metallurgically, there is something called vacancy defect. So if you want to diffuse any material, say this is my copper and this is aluminum, and you want to diffuse copper into aluminum or aluminum into copper. So to have some interdiffusion, this happens because of, it's called vacancy induced diffusion. And as this is happening at a solid state, so atomic diffusion can take a very long time, maybe 1 to 2 hours of time to have the diffusion bond in a very good amount of manner. So if you see diffusion bonding, it's basically the atomic diffusion. Now for ultrasonic welding, what happens in ultrasonic welding? The coalitions is basically produced at the faying surfaces by application of high frequency vibratory energy. So if you see ultrasonic welding, you have some horn kind of thing which have some kind of profile. So in your horn, there will be some kind of sinusoidal profile, and you apply some pressure also. And below that horn, there will be your material which are placed together at intimate contact, and there will be a clamping load here also. So in ultrasonic welding, this horn can vibrate in this horizontal manner, and because of that vibration, it produces a weld because of that oscillating shear force at the interface. So because of that oscillation, there can be some localized temperature rise, which results in some maybe slip or plastic deformation in between the material, and they join together. So for ultrasonic welding, it will be basically a oscillating shear force at the interface. Right now, for FSW, I hope I have discussed it. I have discussed it a lot of times. For FSW, it will be a non-consumable rotating tool, obviously. So for FSW, you have the rotating tool. It can be pinless or with pin also. Let us say we are doing with pin friction stir welding, and the tool will have some kind of plunge depth. The tool will have some kind of plunge depth, so the tool can plunge into the workpiece, and it will rotate over the top surface. right? And due to rotation and plunging force action, there can be some mechanical intermixing in between the material, and obviously there can be some localized, sometimes it can be localized melting also due to high temperature generation. So these are keywords of friction stir welding. So there can be mechanical intermixing, there can be localized melting, there can be, yeah, intermetallic formation also because of diffusion happening. And for explosive welding, it's basically shear deformation due to the impact. So in explosive welding, if you see explosive welding, this is a solid state joining process uh, that uses explosive force to create the metallurgical bond, uh, and it happens in a very short time duration. So for both this FSW and explosive welding, the stress uh, which generates at the interface, that is a function of strain rate and temperature. So uh, whenever the material is at a very higher temperature state, so whenever the material is at a high temperature state, strain rate plays a crucial role, right? So these things are these things can be understood, right?
Yes, sir.
Now in my question two, there are few statements which I have noted down, and then we need to find out which of the above mentioned statements are correct. Now, what is the first statement? The first statement tells that solidification occurs by the nucleation of small grains, which then grow under the influence of thermal condition. Is it true or false? Obviously, this is true. If you see any kind of melting and solidification process, solidification occurs in two phases. So there will be nucleation. My screen is visible, right? Is my screen visible? Are you there? Okay. So solidification occurs in two phases. So there can be nucleation and something called grain growth. So anytime if you are mixing some two metals, so if you see some phase diagram actually, if we try to draw some phase diagram here, so there will be some zone where all the metals will be at liquid state. So this is 100% A, and this is 100% B. So let us assume that we are somewhere in the state where all the metals are at liquid state. So this is at maybe T1. So if we see the microstructure at T1, so all the metals are at liquid state, and then what happens? Uh, so basically, nucleation involves some formation of small stable particles of new phases from liquid. So whenever you want to cool it, so maybe I'm cooling it at temperature T2. So the undercooling is T1 minus T2. So in that liquid state, there will be some formation of stable nuclei here, and eventually with time, the volume fraction of liquid starts to decrease and nucleation of this new particle starts to increase. And with time in a growth state, the stable nuclei obviously will increase. And whenever you are somewhere here in this zone, you'll come up with something called some solid solution of A and B, which we call it alpha plus beta solid solution. So, so first statement is obviously it is true, and then it tells that in the second statement it tells that size of the grains formed is a function of G by R, where G represents temperature gradient and R represents solidification velocity or growth rate. This is also true. So yeah, depending on this temperature gradient and this solid liquid interface velocity rate, or what we call it growth rate, the grain size can vary. So coming to the next statement, it says that higher temperature gradient and lower R, so its lower growth rate, leads to a stable planar solid liquid interface. This is also true. This is also true. Um, so whenever there will be a high temperature gradient, but the growth rate is not high enough, so in at that time you will end up with something called planar interface. But in case if there is if the growth rate is higher, if the growth rate is higher, you finally end up with something called columnar structure. I hope you have seen in welding. Let me draw somewhere here. So if this is if we are doing some arc welding here, so this will be your peak temperature where the melt pool is there, and there will be some heat affected zones here. So if this is at temperature T1 say, and this is at temperature T2, this zone will have the highest temperature gradient. So T peak minus T1 will be higher than T1 minus T2. So wherever the temperature gradient is higher, depending on the temperature gradient, the growth rate will also increase, and it starts to form some columnar kind of dendrite structure. And whenever you are going away from that high temperature gradient zone to low temperature gradient zone, so those microstructures will be unaffected, and there you will end up with something called fine, or maybe yeah, fine microstructure. Now, the last statement states that greater GR, you finally end up with something called finer the solidified cellular or dendrite structure. So, depending on this G into R, So your G was your temperature gradient, and yeah, sorry, this is true. This is also true. This is also true. And then it says that greater GR, finer the solidified cellular or dendritic structure. So if the multiplication value of G and R is higher, it will form finer structure. So this is basically this G into R is determining a cooling rate, right? So obviously, when cooling rate is high, you will come up with something called fine microstructure, and when cooling rate is low, you'll end up with coarse microstructure. These are obviously few of the thumb rules of this welding microstructure physics, basically. So yeah, in question 3, this is a numerical, simple numerical. So it says that an aluminum Fe binary alloy is joined using a gas metal arc welding process, and we need to evaluate the welding speed to achieve planar solidification and weld line. Uh, what are the things given? The things given as temperature gradient is given. So temperature gradient is given as 200 Kelvin per millimeter, and then my diffusion coefficient is given. Diffusion coefficient is given as 2 into 10 to the power minus 3 mm square per second. And yeah, the freezing range is also given. Sorry, this should be the G, right? This is my temperature gradient. My freezing range is given as 20 Kelvin. So what we know from this course is like this: to basically achieve a planar solidification structure at weld line, your G by R value, it should be greater than equal to delta T by uh, DL, right? So if you want to satisfy this equation, so here G is your temperature gradient, which is known, and yeah, we need to find out R. So R will be the solidification velocity, which can be assumed or can be equate with the welding speed also. So your G value is given as 200. Okay, let us do some math first. G by R is equal to, if you are doing some limiting condition, so G by R is equal to delta T by DL. So my R will be dl into g divided by delta t, right? So from here, what will be the solidification velocity? My dl is given as 2 into 10 to the minus 3, that is in mm square per second, that into 200 Kelvin per mm, and that divided by 20. So this will be coming as 2 into 10 to the minus 2 mm per second. Okay.
Yes, sir.
This is understood, right?
Yes, understood, sir.
Yeah. So in next question, it says that in a gas tungsten arc welding process, the numerically determined value of temperature gradient is found to be 335 Kelvin per mm, and your experimentally evaluated welding speed is reported as something called 3.15 mm per second, and freezing range again is given, so which is 50 Kelvin here. So what we need to find out is the thickness of the boundary layer at a steady state at the limiting condition of stable planar solid liquid interface. So what we need to do here, the concept is same here. So if we see the numerically given values are like this, G is given as 335 Kelvin per mm, and then my welding speed is given, so R is 3.15 mm per second, and then my freezing range, yeah. So delta T is given as 50 Kelvin, and then we need to find out thickness of the boundary layer. So what is the thickness of the boundary layer? So it's basically dl by r, denoted by dl by r. So we do the same math here also. Uh, we know that for a stable planar solid liquid interface, G by R obviously happens to be greater than equal to delta T by dl, where my G by R is 335 divided by 3.15, that equal to, it's 50 divided by dl, right? What will be the dl? 335. What will be the unit? It's if it is Kelvin per mm, this is mm per second, Kelvin per second, and this is Kelvin. Yeah, this is coming as mm square per second, right? Is the unit okay? Initially it was Kelvin per second, and then it is coming as hmm. So 50 into 3.15, that divided by 335.
0.47.
It's 0.47. And then, so the DL value is known now, and then TL by R. So TL by R is equal, is giving you the boundary layer thickness. It's coming as 0.47 divided by 3.15. How much it is coming? I think it should come as 0.15.
It's a 0.149, so 0.14.
Okay. Yeah. Understood, right?
Yes, sir.
Now, here we need to, again, we need to find out which of the following statements are true. So it says that homogeneous nucleation is promoted by high degree of undercooling. Is it true or false? So if there is high degree of undercooling, obviously there will be homogeneous nucleation. And then it says that formation of equaxed grains is enhanced by high heat inputs, and this is also true. So whenever your heat input is higher and also welding speed is higher, you end up with equiaxed. Can you tell me if the welding speed is lower, what will happen? So if your welding speed is lower, obviously the peak temperature what it will experience will be higher, right? So peak temperature will be higher, and you finally end up with something called either columnar dendrite or it can be cellular also. Now in your statement 3, it says that with increase in welding speed, the solidification rate of the weld metal also decreases. With increase in welding speed, is it true or false? So These are all thumb rules in your welding physics. So if your welding speeds are higher, your solidification rate will be high. So it starts to cool very fast because of because of high welding speed. The heat input will be low, obviously, and your welding speed is lower. Solidification rates gets reduced. And now the final statement says that high constitutional supercooling promotes columnar dendrite mode of solidification. So if the supercooling is high, why you don't form columnar dendrite? This is also false. So this is false. Let me try another color. Are you agree with these statements? So if your supercooling is higher, it forms something called equiaxed. Right? Okay. So moving to the next question. This is from electromagnetic pulse welding. Uh, but the idea is very basic here. So you have some two infinitely long parallel conductors which are carrying current of I1 and I2. The force generated between the conductors are given. F is given as F is given as 0.5 Newton per meter. And then what is given? What is given? The gap 40 mm. So can you tell me what is the equation of this force for an electromagnetic pulse welding? Do you remember? It is something like this.
Yes, sir.
No? So your mu naught is given, which is the permeability. This and yeah, gap is given. So gap between the conductors is given as 40 mm. So these are all in meter. This is given as millimeter. Yeah. So all things are given here. So we have zero point 0.5 and then 2 into 10 to the minus 6 and then 2 pi into 40 into 10 to the minus 3. So this thing you need to find out. Pi into 40 into 10 to the minus 3. 2 into 10 to the minus 6. How much it is coming? Pi into 40 into 10 to the minus 3. That divided by 2 into 10 to the minus 6. Oh, it's simply 2000 pi. Am I correct? Can you please confirm?
6283.
How much?
6283.15.
6283.1, maybe 2. Okay, should I move to next question? Take some time to read it. So it says that during the solidification of a pure metal, you need to evaluate the value of critical radius. So there is some function of this critical radius and free energy of this to create a surface for spherical particles, right? So we need to evaluate the value of critical radius and the activation free energy, assuming homogeneous nucleation, and following are the values of latent heat of fusion, surface free energy, melting temperature, and degree of supercooling. So what you need to do here, so if you see your free energy as a function of radius, how does it look like? Looks like this, right? Do you remember? So there will have a critical radius. If this is your R star, so basically whenever you talk of some free energy, it composed of something called volumetric free energy and energy needed uh, to create a surface. So basically this equation has been derived for a spherical particle, and your if delta GV is your volumetric free energy per unit volume, what will be the total volumetric free energy then? If R is your sphere radius, it will be simply 4/3 pi r cube into delta GV, right? So this is your volumetric free energy term. That plus something associated with the surface energy. So if gamma is your surface energy, per unit surface area, so this will be 4 pi r square, that into gamma. Understood?
Yes, sir.
So whenever you talk with some free energy, you want to minimize it, right? So you have the function of this total free energy, delta G is your 4/3 pi r cube delta GV plus 4 pi r square. So to find out, it's basically it's called minimization of potential. This is your energy term. So if you differentiate in with respect to r, and then you do some math, what will be the critical radius? Can you give me an expression? It's 4 third pi L cube, so 3 is 4 pi r square. It's 4 pi r square. Yeah. So you finally come up with some expression of this. Am I right?
Yeah, sir.
Now here, what the values are given. Acha, so your delta GV is also can be equated with your latent heat, degree of supercooling, and melting temperature in this sense. Now can you give me a value? So it will be R star is equal to minus 2 gamma that into Tm that divided by L into delta T. So your gamma value is given as 0.25 joule per meter square, and your melting temperature is 660 degrees C. 660 degrees C. L value is given also, which is latent heat of fusion, and this degree of supercooling is also given. So 2 into 1 into 660 divided by. Oh, L is given in minus. So 2 into. Any answer? So for me, it's coming in terms of nanometer.
Yes, sir. Same 1.65.
Agreed?
Sir, temperatures must be at degrees Celsius only, right, sir?
Sorry?
Temperature here Tm must be in degrees Celsius only, right, sir? 660. We can directly
Yes.
use it in. Yes, sir, same answer.
Yes. It's degree C. This value has come, this critical radius.
Yeah, yeah, okay.
So then we need to find out what will be the activation free energy. So you simply put that R star value in your free energy term, uh, and if we do some math there also, we'll finally end up with some equation of this, which is given in the course curriculum also. So in that equation, what was there? Delta G is 4/3 pi r cube delta G V plus 4 pi r square into this. So if we put the value of r here as this, so you'll finally end up with this equation, right? And if you put the values in this equation, what will be the answer? So your gamma is given as, let me do the math also. Okay, so for me it is coming 12.9 into 10 to the power minus 19 joule. Can you please confirm? Let me know if you are getting any other answer. No, I think I'm wrong. This is Have you got any answer? Surface free energy is
Checking,
point. Sorry.
checking, sir. Doing.
Uh, please.
I'm getting 2.85 into 10 power minus 18.
Oh, sorry, got you any answer?
I'm getting 2.85 into 10 power minus 18.
3.35 into
2.85, same answer.
yeah, 2.85. Right. Mine that power is perfect, right? Minus 18.
Yes, sir.
Yeah. So let's move to the last question then. So this is a question from Fiction Star Welding. So it says that an operator wishes to join two 4 steel plates using FSW process using the following process conditions. So here we are using a pinless tool. So the shoulder radius is given as 8 mm, and N is given as 2000, and this plunge pressure is 10 megapascal, and mu is given as 0.4. The catch is here. So you assume a sliding friction condition. So there are two different conditions, I hope you know: sliding and sticking. So for sliding friction, the shear stress will be mu p. And what will be the sticking condition? This k. K is called your shear in stress, which is sigma y by root 3. So here you need to use this formulation of tau equal to mu p. So what will be the value of it? Some elementary heat flux maybe. That is equal to df into r omega, right? So if you are taking this top view of the tool, this is rotating, right? So translation speed will be v equal to r omega. And then what will be the df? So basically, if you want to find the total heat flux, what you need to do? You need to do integrate all over the area, right? It will be 0 to 2 pi and 0 to your shoulder radius is given as we are taking it as rs as of now, and then this is omega r, and for force what it will be? Stress into area, right? So stress is, if your contact shear stress is given as tau contact, that into r d theta into dr. Understood?
Yes, sir.
I'm trying to derive the formulation how it is coming. So here it is 0 to 2 pi and then 0 to rs. You are given tau as mu p. So mu p into omega r square dr into d theta. Am I right? So that is equal to 0 to 2 pi and 0 to, let us put the value now. So it's 8. And then omega is 2 pi n by 60, which is not a function of r or d theta, and mu p is also known value. So yeah, we can keep it outside of the integration. Mu p 2 pi n by 60, 0 to 2 pi, 0 to 8 r square dr into d theta. Now mu is your 0.4, that into 10, that into 2 pi into 2000 by 60, that into, this is your constant term, that into 0 to 2 pi. This is r cube by 3, so 8 by 3 into d theta. So total heat flux will be in terms of what? And then if we do some math, can you give me some value? 0.4 into 10 into 2 into pi 1000 60 37. Can you tell me you are getting same value now?
Yes, sir. 14024. So 14 to 10 power 3.
Yeah, great. Okay. Any confusion? Yeah, I'm done from my side. So if you have any confusion, you can ask me, or yeah, in the last session I gave my mail ID also. Now the videos are getting uploaded properly, right?
Yes, sir. I checked it. So the weeks is good. Like the
Yes.
PPTs are visible in the video. So I checked it. Yes, sir.
Yeah. Okay. So if you do not have any confusion, we can finish it here.
Yeah. Okay, sir. Sure.
Okay. Bye bye.
Thank you so much, sir. Good evening.
Thank
Bye.
you. Thank you. Bye.